Hello students, in this session we are going to study the limitations of Euler's theorem. Before we define the limitations of Euler's theorem, let us think of the slenderness ratio, redefine the slenderness ratio. Slenderness ratio. We have shown that slenderness ratio is given by the length of the column by the least modulus of rigidity of the material, right? But we have also seen that the effective length, we have also studied the effective length or equivalent length LE, that for different types of end conditions, the effective length is different. Like suppose for this type of end condition, which was the case 1, this type of end condition that hinge joint was there, the effective length was equal to the length of the column itself, right? Second case, we have taken the free end, that if the end is free, then the effective length was 2 times the total length of the column. Third case, we have taken that if both the ends are fixed, the effective length was half the total length. And fourth, one end hinged and other fixed, this type of case, and the effective length is L by root 2. So we have taken these cases. In these cases we have find out the effective length, right? So slenderness ratio is now redefined, that slenderness ratio is given by the effective length, that this L is basically the effective length. For hinge joint it is okay, length of the column, but for others this is the effective length upon the K minimum, radius of gyration. Slenderness ratio is now redefined as effective length upon minimum radius of gyration, right? You should remember these things first before we go to the limitations of Euler's theorem. Now let us proceed to the limitations of Euler's theorem. So what are the limitations of Euler's theorem? We know the Euler's load is given by pi square EI upon LE square, right? Effective length we are using here, LE square, where I is the moment of inertia of the body, that is equal to area times radius of gyration square. Area times radius of gyration square. So this is the moment of inertia, right? So this implies that the Euler's load will be given by pi square E, I is AK square upon LE square. So this will be equal to pi square AE upon LE by K whole square, where LE by K is the slenderness ratio. We are taking K as the minimum radius of gyration. So Euler's load will be equal to pi square EI AE upon slenderness ratio whole square. Right? So this is the Euler's load, right? Euler's load. From here, slenderness ratio can be written as under the root pi square AE upon PE, Euler's load, right? And this will be equal to PE by A is stress, so that will be equal to pi square E by sigma, right? Where stress load upon area is the stress, right? This is the load, Euler's load, this is the area, so the P by A is stress, right? Stress at which the buckling takes place or the material fails, right? The maximum, because we are talking about the maximum load, Euler's load, right? So we are talking of the stress, right? Sigma E, Euler's stress or stress, right? And you know that for some of the materials, like, so slenderness ratio formula we are writing here, pi square E upon sigma E. This formula you should remember, right? Slenderness ratio is equal to pi square E upon sigma E. Now, talk about the mild steel, or take any material like mild steel. So, if we are talking about the mild steel, there are some typical figures, typical values are there for sigma E and E. Sigma E is the stress where the mild steel fails, right? And in general, the stress where mild steel fails in compression is given by 320 megapascal. From experiments we know these things, that the stress is 320 megapascal, and the modulus of elasticity of steel is 210 gigapascal. These are the typical values. These are the typical values which are used in the design of steel, that the stress at which the mild steel fails is 320 megapascal. This is the maximum stress which it can take from the experiments we know, and the modulus of elasticity is 210 gigapascal. So if we use this value in this equation, if we put these values in equation number 1, what we get? We get that slenderness ratio will be equal to under the root pi square multiplied 210, this is gigapascal, 10 power 9 pascal, divided by sigma E, 320 megapascal, this is 10 power 6 megapascal, right? Solve it and you will get the slenderness ratio as, and these stresses should be less than 320. Stress should be less than 320, right? So I am writing here, this is less than equal to 320. If this is less than equal to 320 and it is denominator, then slenderness ratio should be greater than equal to these values, right? So I am writing here greater than equal to. If it is less than equal to, then it should be greater than equal to, because it is in denominator. So slenderness ratio should be greater than this value, right? So slenderness ratio should be greater than equal to this value, right? And this is around 80. It means that this formula has a limitations, that it is applicable only for the slenderness ratio greater than 80 for steel, if we are talking about steel, and for many materials there is a certain limitations. For all materials there is a limitations where this formula can be applied. So this formula can be applied only for slenderness ratio greater than 80. So theoretically Euler's theorem is applicable only at slenderness ratio greater than equal to 80, right? For steel, we are talking about steel, we are not talking about here, we are taking an example of steel, which is the typical material used in mechanical engineering. But practically it is found that it gives error-free results when the slenderness ratio is greater than 120, right? Because it is not considering the crushing stresses, right? That's why error-free for practically errorless results with Euler's theorem are obtained at slenderness ratio greater than 120. When the slenderness ratio is greater than 120, here actually errorless results are obtained with Euler's theorem, but theoretically with using the theoretical calculations, we are getting the slenderness ratio greater than 80. Only then we can apply the Euler's theorem. So this is the limitations. This is one of the limitations, major limitation of Euler's theorem, that it is applicable only for long columns and the columns which has slenderness ratio greater than 120.